Tonight, we're going to explore one of the most demanding journeys a human being could ever attempt. For centuries, we have looked at a single reddish point of light and dreamed of standing on its surface. Mars, the one world beyond our own that a person could plausibly reach and survive. At its closest, a gap of roughly 34 million miles, and the destination we keep sending machine after machine to explore. But here is what most people don't realize. The real question was never whether we could build a rocket large enough to get there. Not whether we will reach Mars, but whether the fragile human beings we send will survive the years it takes to arrive, to work, and to come home. By the end of tonight, you're going to understand why the greatest danger of the journey is not an exploding rocket, but the slow toll it takes on the human body and mind. How a crew would cross the vast emptiness between the planets with no possibility of rescue, and what the word home might come to mean if we ever truly left the only world that made us. Before we get started, take a second to like and subscribe. It really helps the channel. Now, let's begin. The fascination became something more once telescopes grew powerful enough to reveal that Mars was not simply another light in the sky, but a world with features that could be watched and measured. That mattered because the other planets offered very different pictures. Venus was hidden beneath a permanent blanket of cloud, giving early astronomers almost nothing to study on its surface. Jupiter and Saturn revealed storms, bands, and rings, but they were enormous gaseous worlds with no familiar ground waiting beneath the telescope. Mars kept giving observers something easier to imagine. Its surface was visible, bright regions appeared near the poles, dark markings crossed the rust-colored terrain, and as astronomers returned to the planet season after season, some of those features seemed to change. The polar caps grew during the Martian winter and retreated during summer. Dark patches appeared to expand and fade across the surface. To modern eyes, none of that proves anything extraordinary, but to 19th century astronomers searching for another living world, the resemblance to seasonal change on Earth was difficult to ignore. Slowly, observation began turning into interpretation. If the white regions were ice, perhaps they melted. If the dark regions changed with the seasons, perhaps vegetation was responding to that water. And if Mars had water, seasons, and a solid surface, perhaps the planet was not merely similar to Earth in appearance. Perhaps something lived there. In the 1800s, the Italian astronomer Giovanni Schiaparelli mapped a network of lines across the surface and called them canali, the Italian word for channels, simply meaning grooves or natural cuts in the terrain. The American astronomer Percival Lowell took that one word and ran far past anything the evidence could support. He translated canali as canals, and canals meant builders. Lowell became convinced Mars was crisscrossed with an engineered irrigation network, constructed by an ancient, dying civilization desperately pumping meltwater from the polar caps down to a parched equator to keep itself alive. Lowell was wrong. Not evidence of a dying civilization. A trick of the eye and the shape of what people wanted to see. But the wanting mattered more than the mistake. It lodged itself deep in human culture and never fully left. Humanity wanted Mars to be inhabited, wanted it to be alive, the way we are alive. And even now, more than a century later, the question of whether it ever was has not been closed, a possibility that has not been ruled out. Every telescope pointed at that reddish light was, in its own small way, a species trying to understand itself by looking outward. But here's the practical reason Mars keeps pulling at us, and it turns out to be simpler than the myth. By the standards of the solar system, Mars is close. At opposition, when Earth and Mars line up on the same side of the Sun, the gap between the two worlds can shrink to roughly 34 million miles. Picture driving that distance without ever stopping. At highway speed, the trip would take more than 60 years. Circle the equator instead, and you would need to go around more than 1,300 times to cover the same ground. That is Mars at its nearest, and it is still an almost unimaginable gulf. Now compare it to the alternatives. Jupiter, even at its closest approach, sits nearly 370 million miles away. Neptune is billions of miles beyond that, a distance that stops behaving like a number and starts behaving like an abstraction. Mars is not close in any ordinary sense of the word. It is close only because everything else in the solar system is so much farther. That is what makes it the stepping stone, the first real destination beyond the Earth-Moon system that a human being could plausibly reach and survive. And it is not only distance. Mars behaves in small and startling ways like a world we already know. A Martian day runs 24 hours and 37 minutes, barely longer than our own, close enough that a body's internal clock could almost keep time by it. Its axis tilts about 25 degrees against the sun, close to Earth's 23.5, which means Mars has seasons the way we do. Spring sliding into summer, autumn settling into winter, just stretched out across a longer year. Since a single trip around the sun that takes nearly twice as long as it does here. It has an atmosphere, thin and fragile, mostly carbon dioxide, the same gas we exhale with every breath, but an atmosphere nonetheless, thick enough to carry weather, thin enough that it could never carry us. It has a rocky, solid surface a person could stand on, not a churning ocean of gas like the giants farther out. It has water, not flowing, not easy to reach, but locked as ice at the poles and bound into the soil itself, waiting. It has a day. It has seasons. It has ground beneath it and water within it. Harsh, frozen, deeply alien. And yet, of every other world in this solar system, the one that feels, distantly, like it could someday be understood, like it could someday be a second home. The word home is where the picture gets complicated. Going to Mars is not like moving to a new city, or even a new continent. It is not like anything humanity has ever attempted. A journey with no return flight waiting on the tarmac if something goes wrong. No embassy to call, no Coast Guard to send a boat, and the honest admission, from the astronauts training for it and the engineers designing the hardware that might carry them, is a simple one. We do not have all the answers yet. What exists instead is real plans, drawn up and revised for decades. Bold technology, some of it already flying, some of it still on paper. A long history of solving problems that once looked permanently unsolvable. From powered flight to a footprint on the moon to a robot the size of a car driving itself across another world. The plans are serious. The technology is bolder than anything that has ever left the ground. But no one who works on this mission, not the engineers running the simulations, not the astronauts logging thousands of hours preparing for a trip they may never complete, pretends to know exactly what those years away will ask of a human body and a human mind. That gap between the dream and the honest admission is the real story here. More than any rocket or any red patch of ground could be on its own. Mars did not earn its hold on us by being easy. It earned it by being close enough to reach and far enough to demand everything a person has. A reddish point of light that a shaky, handmade telescope, once barely resolved into a disk, has pulled an entire species toward the edge of what it knows how to do. Wanting to go is the easy part. What lies between wanting and arriving is a distance measured in something far harder than miles. The only real comparison we have is the moon, and even that comparison breaks almost immediately. In 1969, the Apollo astronauts crossed roughly 239,000 miles to reach it, a trip that took about 3 days. That is more than 9 trips around Earth's equator, laid end to end, just to get there. It sounds like a long way, until you set it beside the destination that actually matters here. And because the moon sits so close by cosmic standards, mission control could still talk to the astronauts in something near real time, a radio delay of just over 1 second each way. Neil Armstrong spoke, and Houston answered almost as if he were standing in the next room. It felt like a slightly laggy phone call, not a conversation across a real gulf. Every plan for reaching Mars gets measured against that memory. Every one of them fails the comparison. Mars offers no such comfort. Earth and Mars do not move around the sun at the same pace. Earth completes one orbit every 365 days. Mars takes 687. Because the two planets keep falling in and out of step with each other, the distance between them is never fixed. There is no single number you can memorize and carry with you. Sometimes, they sit on the same side of the sun, and the gap shrinks. Sometimes they sit on opposite sides, with the sun itself in the way, and the gap stretches past 250 million miles. Averaged across a full cycle, the two worlds sit around 140 million miles apart. That is nearly 600 times farther than the moon ever gets from Earth. The distance a spacecraft has to cross depends entirely on the moment it leaves, which is exactly why nothing about this journey can be scheduled casually. Even light cannot close a gap like that quickly. Light moves at about 186,000 miles every second, the fastest anything in the universe is allowed to travel. Point a radio dish at Mars, and the signal you send is already traveling as fast as physics permits. No faster route exists, no shortcut, no clever engineering fix. And still, a signal leaving Mars takes somewhere between 3 and 22 minutes just to reach an antenna on Earth, depending on where the two worlds happen to sit in their orbits that day. 22 minutes does not sound like much, until you need it. How do you plan a rescue when the fastest possible warning takes 22 minutes to arrive? How do you talk someone through a crisis one sentence at a time, each reply landing decades after the question that prompted it feels finished? Mission planners have had to build an entire philosophy of self-reliance around that single, stubborn number. In February 2021, as the rover Perseverance descended toward the Martian surface, the engineers watching from mission control had already lost any ability to help. The landing sequence itself takes minutes, the signal confirming it takes longer, so the room sat in silence for 11 full minutes, not knowing whether the spacecraft had touched down safely or shattered against the rock, waiting to learn something that had already happened, one way or the other, long before the news arrived. Every camera in the room was pointed at engineers who could do nothing but wait, because the machine on Mars had already lived or died before anyone on Earth even knew the descent had begun. Now, picture that 11 minutes belonging to a person, not a machine. An emergency on the way to Mars means radioing home, explaining what has gone wrong, and then waiting 20 minutes or more before anyone on Earth can even begin to respond. By the time a reply comes back, the situation described in it may no longer exist. Not a phone call, an exchange of letters, each one landing long after the moment that prompted it. There is no cavalry, there is no hotline. Whatever happens out there, the crew meets it alone, because by the time help could be dispatched, the crisis has already resolved itself, one way or the other. That single fact reshapes everything about who gets chosen for a mission like this, and what they are trained to do without permission from home. A crew bound for Mars cannot simply follow instructions relayed from Earth the way every previous crewed mission has. They have to become their own mission control, thousands of decisions deep into a journey no one on the ground can watch happen in real time. Every prior human spaceflight, from Apollo to the space station orbiting overhead right now, has had a safety net stretched underneath it, a voice on the line, a rescue vehicle on standby, a plan B built by people who could see the problem unfolding as it happened. Mars removes that net entirely. But here's where it gets stranger. Distance is only half of what stands in the way. The most fuel-efficient route to Mars is called a Hohmann transfer, a long looping orbit that arcs around the inner solar system instead of cutting straight across it. It is not a straight line from one planet to the other. It is a wide, curving arc timed so that Mars is waiting on the far side when the spacecraft finally arrives. Even using the most advanced propulsion currently under serious development, that route takes roughly 7 months, one direction. 7 months sealed inside a vessel smaller than a house, watching Earth shrink into a single point of light. Then, once the crew finally reaches Mars, orbital mechanics forces them to wait there, often a year and a half or more, before the two planets line up again for the trip home. Not because the mission is finished, because the sky itself is not yet arranged correctly for the return leg. Another 7 months follows after that. Add it all together and the total mission runs somewhere between 2.5 and 3 years. Wait, 2.5 years. Away from every person, every place, every ordinary texture of life on Earth. Farther from home for longer than any human being in history. And the departure itself cannot simply happen whenever anyone decides it should. Because Earth and Mars move at different speeds, a genuinely efficient trajectory only opens once every 26 months, when the geometry between the two planets briefly lines up. Miss that window and the wait is not measured in weeks. It is another full 26 months, long enough for a newborn to grow into a toddler taking its first steps before the numbers align again. So the spacecraft, the crew, the food, the fuel, the training, every piece of it has to be completely ready the moment that window opens. Not almost ready, completely ready. No grace period, no second chance that year. The cosmos runs on its own timetable, and every human plan simply has to fit inside it. NASA and its partners have already mapped windows stretching into the late 2030s and beyond. SpaceX has talked about attempting a crewed mission as early as the late 2020s, using the Starship system now in development, though those dates have shifted before and will likely shift again, as ambitious timelines in spaceflight so often do. What is certain is simpler than any specific year. The window will come, and when it does, every second leading up to it will count. Behind every one of those constraints, the fuel calculations, the 26-month clock, the 22 minutes of silence, sits a person who has agreed to live inside them for years. The window, the delay, the distance, all of it is only math until you remember it has to be carried by someone. This is not only a story about rockets and trajectories and radiation. It is a story about real, fragile, complicated human beings who would leave everything they know behind for years, inside the most hostile environment imaginable. The crew itself is almost certainly small. Current mission concepts converge on somewhere between 4 and 6 people, just enough to cover the skills a Mars expedition actually needs, and no more. A commander, a pilot, a flight engineer, a medical officer, a geologist, and possibly a biologist trained to recognize the faintest hint of something that was once alive. Any larger and the mission drowns in its own logistics. More food, more water, more oxygen, more mass that has to be launched, fueled and carried across the gap between the two worlds. Small crews do not mean small demands. Each person selected has to be technically brilliant, which is almost the baseline now among astronaut candidates, and psychologically robust in ways that are genuinely rare. They must function as a team under sustained stress, isolation, and uncertainty for years at a stretch. They must make life or death decisions with no guidance from Earth, holding together at the exact moment everything inside them might be screaming to panic. What does that actually require? Not just calm under pressure, calm that lasts. Not just competence in one field, competence deep enough to substitute for an entire hospital, an entire engineering team, an entire mission control room, because on this trip, those things do not exist anywhere but inside the crew itself. Nobody has flown a Mars mission yet, so planners study the closest thing this planet actually offers. Researchers look at crews wintering over at Antarctic stations, among the most isolated postings on Earth, months of darkness, no chance of evacuation, no way out until the ice itself allows it. It is not Mars. There is still air outside the door, still a horizon that ends somewhere familiar. But the psychological terrain is close enough that planners treat the data as a genuine warning. The patterns that show up there are patterns mission planners take seriously. Interpersonal tension that builds slowly, then sharply. Sleep quality that deteriorates. Cognitive performance that quietly dips. In ways the person experiencing it may not even notice happening to them. One finding worries mission psychologists more than the rest. Researchers call it the third quarter effect, a measurable drop in morale and motivation that tends to hit roughly 3/4 of the way through a long, isolated deployment. Not at the start, when everything is new and adrenaline carries you. Not at the very end, when the finish line is close enough to pull you forward. Right in the exhausted middle, when the novelty has worn off completely and the end still feels impossibly far away. On a Mars mission, that slump would not arrive somewhere survivable and familiar. It would arrive on the surface itself, out on the barren, frozen ground, with the crew still needing to work, still needing to think clearly, still needing each other. And here is the part that is easy to miss underneath the statistics. These people would know all of this before they ever agreed to go. They would have read the isolation studies. They would have sat through the psychological briefings built to find their breaking points. They would have run simulations designed specifically to see what remained standing once the pressure was applied, watch colleagues wash out, watch themselves come close to washing out too, and still, knowing exactly how the mission could fracture them, they would raise their hand. They would say yes to 7 months sealed in transit, a year and a half stranded on a hostile world, 7 months back, and to every single thing that could go wrong along the way. Why would anyone agree to that? Because it is not really a new impulse. It is an old one wearing a new destination. For hundreds of thousands of years, small bands of ancestors followed river valleys into land no one in their group had ever seen, not knowing what waited past the next ridge, only that something did. None of them had a guarantee of food on the far side, or water, or safety. They went anyway, generation after generation, because staying in a known and shrinking place has never been the whole of what this species is. The horizon kept changing shape. First a valley, then a coastline, then an ocean, then a continent, then the edge of a map with nothing drawn past it. Now the horizon is a reddish point of light that swings across the night sky. The distance has changed almost beyond recognition. The impulse pulling people toward it has not changed at all. We are explorers at the level of instinct, and Mars is simply the next horizon far enough away to matter. It is tempting to think the mission's greatest vulnerability is mechanical. A fuel line, a heat shield, a seal that fails under stress no engineer fully anticipated. It is not. The most fragile part of the entire endeavor is not built in a factory and cannot be tested on a bench beforehand. It is the human being riding inside the capsule, carrying a nervous system shaped by one planet into an environment that planet never prepared it for. And the strongest part of the mission turns out to be exactly the same thing. The willingness of that same fragile person to go anyway, eyes open, knowing the cost in advance. That willingness would be tested first in the most immediate way there is. Long before isolation or distance ever had the chance to work on a person, before any of it turned into something abstract and slow, that yes would have a date attached to it, and a countdown attached to the date. That countdown arrives after years, sometimes the better part of a decade, of training folded so deep into the body it stops feeling like training and starts feeling like instinct. Every switch, every checklist line, every abort procedure rehearsed in simulators until the sequence needs no conscious thought at all. Goodbyes said with the quiet understanding that the next hug, the next familiar voice in the same room, might be 3 years away, might never come at all. The crew lies flat on their backs inside the capsule, strapped down so tightly that a full breath takes effort, listening to numbers counting towards 0. The ceiling above them a wall of switches and displays instead of sky. The machine beneath them is Starship, the vehicle most current Mars plans are built around. Fully assembled, it stands about 120 meters tall, taller than the Statue of Liberty with its pedestal, taller than the Saturn V that once carried astronauts to the moon. Fueled and ready, the whole stack weighs close to 5,000 metric tons. About as much as 14 fully loaded jumbo jets welded into a single tower and aimed at the sky. Almost none of that mass is the small pressurized volume the crew is actually riding inside. A compartment lost inside a structure built almost entirely to hold and burn fuel. At the base, the Super Heavy booster produces roughly 74 meganewtons of thrust at liftoff, the combined push of about 33 Saturn V's firing at once. Put another way, it is close to detonating 300,000 pounds of TNT every single second, continuously, for several minutes straight, not as a single blast, but as a controlled, sustained burn aimed straight down at the pad. That is the price of leaving Earth's gravity behind. It is tempting to picture that tower as mostly spacecraft, a crew capsule wrapped in machinery. It is not. Somewhere between 90 and 95% of that mass is fuel. The crew, their supplies, their equipment, all of it rides as a sliver on top of an ocean of propellant. To go up, you have to burn down. That arithmetic has defined spaceflight since the first rocket ever left the ground. At 0, the engines ignite. The sound reaches the body before it reaches the ears, a pressure that rolls up through the pad, through the structure, through the seat, into the bones. The thrust tips past the weight of the vehicle and it begins to climb. Slowly at first, then faster. Acceleration presses the crew back into their seats at several times their own body weight. Faces distort. Vision narrows at the edges. Every breath takes effort. Everything vibrates, the whole vehicle shuddering as it fights its own weight, and the air resisting it. About 60 to 90 seconds after liftoff comes max Q, the point where the vehicle is climbing fast enough and the lower air is still thick enough that the two forces pushing against the hull reach their highest combined stress. This is the moment the vehicle is most likely to be torn apart by its own speed, not by anything wrong with the machine, simply by the physics of moving that fast through air that thick. The engines briefly throttle down, easing the load, buying the airframe a few seconds of relief before pushing forward again. Past max Q, the atmosphere thins fast. The sky slides from blue to deep indigo to a black with no softness left in it. The stars stop flickering. They just sit there, hard points of light, unblinking, the way they only look from above the air, and the crew, still pinned to their seats, catches the first glimpse of the darkness that will surround them for years. The booster finishes its work, separates, and tumbles back toward the landing site, where in the newest designs it is caught mid-air by two enormous mechanical arms reaching out from the launch tower, the same booster that just threw a 5,000-ton vehicle off the planet, snatched out of the sky like a caught football. A decade ago, that idea belonged in science fiction. Now it is closer to routine, one more rehearsed step in getting a crew off the ground. Above it, the upper stage keeps firing, climbing toward an orbital velocity of roughly 28,000 kilometers an hour, fast enough to cross the entire continental United States in under 10 minutes. At that speed, the crew is not climbing away from Earth's gravity, not escaping it. They are falling toward the ground fast enough, and the ground is curving away beneath them fast enough that they never actually land. That is what orbit is. Perpetual falling that never connects. The violence of the last several minutes gives way, all at once, to something closer to stillness. The engines cut, and everything that was not strapped down a moment ago begins to drift. A checklist pinned by gravity seconds earlier floats free. Bodies pressed hard into their seats for minutes suddenly weigh nothing at all. It feels for a moment like arrival. It is not. But here's the part most people miss. Reaching orbit is not the finish line. It is barely the starting line. A Mars mission does not simply arrive in orbit and point itself outward. It has to be refueled there first. In the current designs, particularly the Starship architecture, the ship that just carried the crew off the ground does not have nearly enough propellant left to reach Mars. It has to be topped off in orbit before it can even attempt the burn that leaves Earth for good. More tankers launch behind it, each one carrying fuel instead of people. Each one required to rendezvous with the crew vehicle in vacuum and transfer that propellant from one spacecraft to another, hundreds of kilometers above the atmosphere, out of sight of any camera on the ground. No crewed mission in history has ever done this at this scale. It is one of the most complex, least visible parts of the entire journey, unfolding quietly while the world below assumes the hard part is already finished. Every day spent waiting for the refueling to finish is another day exposed to micrometeoroids, fragments of debris moving fast enough to pierce a hull, to radiation, to the ordinary mechanical failures that can happen to any machine sitting in space long enough. None of it is dramatic in the way launch was dramatic. There is no crowd for it, no broadcast countdown, just controllers and automated systems working through a checklist far from any camera. All of it still has to go right, tanker after tanker, transfer after transfer, before the engines are even cleared to attempt the burn that sends the ship toward a world tens of millions of miles away. When that burn finally comes, it does not look like launch. There is no roar, no fire visible from the ground, no crowd holding its breath. This is the Trans-Mars injection, the engine firing that bends the ship's path away from Earth and commits it to Mars for good. The engines fire once more for the last time in Earth's gravitational neighborhood, and telemetry confirms the trajectory is set. Then, the engines cut off. The vibration stops. No siren, no announcement. Just the silence of deep space settling over the capsule like something heavy and soft at the same time. This is the moment that actually starts the voyage. Not the fire of liftoff, not the strain of max Q. This quiet one. Earth begins to shrink, and not the way it shrank during launch, when the coastlines and the clouds were still close enough to name. It shrinks into something smaller, something fragile looking, the kind of small that makes you want to protect it without knowing how you ever could. And it is only going to keep getting smaller from here. Days become weeks, and Earth keeps doing exactly that, getting smaller. Somewhere in those first weeks after the burn, Earth and the Moon start to look like what they actually are from out here. 2 points of light traveling close together, one bright, one dim, hanging side by side against a field of stars that hasn't shifted in living memory. Weeks after that, even the pair comes apart. Earth becomes 1 point of light among many, no longer obviously different from any star around it. Carl Sagan gave that point a name once, the pale blue dot. A single frame looking back at the only world our species has ever called home. Out here, the description stops being poetry. It becomes plain fact. The crew is, by any measure that matters, alone in deep space. Astronauts who spend time aboard the space station often come home changed by something researchers call the overview effect. The shift that comes from watching the planet turn beneath you with no borders drawn on it. Just weather and coastline and light. Old arguments start to look small. National lines stop making sense. Whole conflicts, viewed from that height, start to look like something drawn on the same fragile skin. But that effect is measured from a few hundred kilometers up. Close enough that Earth still fills a third of the sky. Close enough to get home again in hours if it had to. Out past the Moon, none of that safety is left underneath the feeling. The same shift happens, only stretched further and cut deeper. Because there is no window to walk back to with Earth filling the view again, and no version of the view that gets bigger again on this leg of the trip. Every hour, the light gets a little dimmer, a little steadier in its smallness, until it stops looking like a place at all and starts looking like a fact. What does that do to a mind? What happens when the world that shaped every instinct you carry shrinks down to a single point, and then eventually disappears into the general scatter of stars? Here's what surprises even the researchers who study this for a living. The sharpest danger of this stretch of the journey does not come from a collision, a rupture, anything that would show up on a damage report. It is quieter than that. The human mind was not built for this, not built for it in a specific physical sense. Hundreds of thousands of years shaped our brains on open ground, under an open sky, tuned to changing seasons, to a small circle of familiar faces, to a horizon a person could actually walk to. We are creatures built around place, around belonging, around people close enough to touch. Out here, none of that exists. No season turning, no new face for years at a stretch, no ground beneath the feet at all. The body keeps expecting a horizon and finds a hull instead. The same 6 walls, the same handful of faces, month after month after month. Researchers already know what that absence does to a person, because the data already exists, gathered from the closest environments Earth has to offer. Crews aboard the space station, teams wintering over in Antarctica through months of unbroken darkness. Submariners sealed beneath the ocean for half a year at a time, no sky at all, not even a point of light to watch shrink. The pattern repeats across every group studied. 3 very different environments converging on the same conclusion. Attention narrows, small irritations grow teeth. The quiet skill of reading another person's mood, catching frustration before it turns into something worse, degrades without anyone quite noticing it happening. Sleep frays first, and unlike the irritability, it tends to stay fragile for the rest of the mission rather than settling back down. None of it announces itself as a crisis. It arrives as a slightly shorter temper here, a slightly longer silence there, small enough at first to explain away, and that is exactly what makes it dangerous over years rather than weeks. The one thing that might ease any of it, a familiar voice answering back in real time, is already gone by this stage of the flight. The delay that turned a phone call into something closer to an exchange of letters has only grown since launch. 10 minutes each way now. Soon, 15. soon 20. A message sent home in a low moment lands in an empty room, and whatever comes back in reply arrives long after the feeling that prompted it has already passed. Not a conversation anymore, a record of feelings that have already moved on by the time anyone reads them. So, what do you do about a danger that never shows up on a hall sensor, never trips an alarm, never announces itself the way a cracked seal or a failing pump would? There is no gauge for loneliness, no warning light for a mind wearing thin. Space agencies have spent decades building an answer anyway, not a cure. A set of hard-won countermeasures, tested against exactly this kind of erosion, refined mission after mission, analog after analog, because the problem was never going away on its own. First, selection. Crews are screened deeply for psychological resilience long before anyone reaches the launch pad, watched under simulated pressure for the way they hold together, rather than simply the way they perform. Second, structure. The spacecraft carves out small private spaces, genuine personal time, work and rest schedules built around the mind's limits and not only the body's. Third, escape of a kind. Some designs include virtual reality gear the crew can put on and, for 20 minutes at a stretch, stand somewhere else entirely. A forest, a beach, a living room with rain against the window. The ordinary Earth the flight took away from them, borrowed back in small doses. None of it is a perfect fix. The people who built these systems are the first to say so. The way any honest researcher will tell you a countermeasure only softens a problem it cannot remove. But every one of these countermeasures exists because of a lesson learned again and again across decades of watching people endure isolation on ice, underwater, and in orbit. The mission's most fragile part was never a valve, a seal, a length of wiring. Not the fuel lines threading through the hull. Not the life support racks humming quietly behind the walls. The person breathing the air those racks produce. That fragility is not a flaw hiding in the plan. It is the plan's most honest feature. The one thing every engineer and every researcher on this problem refuses to design around instead of facing directly. A heat shield can be tested to failure in a lab, burned and measured and rebuilt until the numbers hold. A mind cannot be tested that way, not without cost, which is exactly why the people responsible for this journey keep circling back to it, mission after mission, rather than treating it as solved. And the mind is not the only thing under quiet siege out here. Something else is already moving through the capsule walls, through the crew's bodies, through their cells, right now, at this very moment, and it has never once cared whether anyone notices. It has no flash, no impact, no sound striking the hull. It is background radiation, charged particles slipping through metal, through skin, through the twisted ladder of DNA inside every cell, nicking the code the way weather nicks stone, one small strike at a time. This happens on Earth too, every hour of every day, and nobody notices because the damage is undone almost as fast as it happens. Tiny repair crews inside every cell, stitching the code back together, quietly, correctly, billions of times across a single life. Earth hands that protection out for free. Leaving Earth means finding out what it actually costs. The planet shields you twice. First, the magnetosphere, a magnetic bubble generated deep in the churning iron of Earth's outer core, reaching outward tens of thousands of kilometers, several Earths wide from end to end, catching the sun's stream of charged particles and steering them around the planet instead of through it. Strip that shield away, as happened to Mars billions of years ago, and the sun's wind peels an atmosphere off a world in slow motion, stripping it away molecule by molecule until almost nothing is left. Not a fade, a wound that never heals. Second, the atmosphere itself, thin as it feels standing inside it, works out to roughly 10 meters of water sitting overhead at all times, close to 3 stories of liquid weight, absorbing and scattering whatever the magnetic field lets through. 2 shields, one magnetic and invisible, one made of the very air a person breathes without ever thinking about it. Clear Earth orbit, and both disappear at once. What used to happen to sunlight and solar wind now happens directly to the people sitting inside the hull. two distinct threats wait in that gap, and they behave nothing alike. The first, solar energetic particles, are fast protons thrown off the sun during flares and eruptions on its surface. Instruments can catch the first signs of an eruption and start a clock, but the warning is short, sometimes as little as a few hours, less time than a single work shift, barely enough to react. A strong enough event, unshielded, can deliver a lethal dose inside that same short window. Apollo's crews were lucky. Several major solar events struck during those years, and the Apollo 16 astronauts happened to be safely between missions, back on Earth, when one of the largest hit. A crew caught in open transit would not have had that luck. That is why every serious Mars design includes a storm shelter, a small, heavily shielded compartment built into the ship, cramped, unpleasant, the kind of space nobody wants to spend days folded inside. But when the alarm sounds and the clock starts counting down from a few hours, cramped and unpleasant becomes the difference between coming home and not coming home at all. The second threat gives no warning at all. Galactic cosmic rays are not solar. They are atomic nuclei, stripped bare of their electrons, flung to nearly the speed of light by the most violent events the universe produces. Supernovae, colliding neutron stars, the jets thrown off spinning black holes, crossing the galaxy for millions of years before one of them happens to intersect a spacecraft. No instrument sees them coming. No shelter schedule can be built around them. They simply arrive, one at a time, constantly, for the entire length of the journey. And here the obvious fix fails. More shielding should mean more safety. Not always. When a fast-moving cosmic ray strikes a thick wall, it does not simply stop the way a bullet stops in a sandbag. It can shatter the atoms of the wall itself, breaking into a cascade of secondary particles, a shower of new radiation sometimes worse than the original ray. Past a certain thickness, for certain particles, more material makes the danger worse instead of better. Bolt on more armor, and you can build the exact hazard you were trying to keep out. Numbers make the danger concrete. Curiosity's radiation assessment detector, an instrument built specifically to measure this threat, recorded doses during its 8-month robotic cruise to Mars in 2012, and again on the surface afterward, the first detailed picture anyone had of what the environment actually does. Cruise alone delivered roughly 100 milligray, the standard unit for absorbed radiation dose, more than an astronaut absorbs across 6 months aboard the space station. On the surface, with no magnetic field and barely any atmosphere overhead, the daily dose runs several times higher than what station crews experience floating in low orbit. Stack a 7-month transit each way onto a surface stay measured in months, and total mission exposure pushes against, and in some mission designs exceeds, the career radiation limits space agencies set from their own statistical models of lifetime cancer risk. Limits built to keep an astronaut's odds of dying from radiation-induced cancer within an agreed, acceptable margin. Crossing that line does not guarantee illness. It quietly raises the odds, for years or decades after the mission ends, long after anyone is watching for it. That already sounds like the worst of it. It is not. The newer, stranger finding concerns the brain itself. Rodents exposed to simulated galactic cosmic ray environments in laboratory studies showed measurable changes, reduced memory performance, heightened anxiety-like behavior, structural changes inside brain tissue itself. The particles were not just passing through. They were altering the architecture underneath thought itself. Not damage to a knee or a lung. Damage to the very tissue the mission depends on to think clearly, decide correctly, and land safely on another world. Researchers are careful here. Rodent brains are not human brains, and nobody studying this claims the findings translate directly. Not yet. But the underlying physics is not in question. Heavy, fast-moving particles cause a tangled, clustered kind of damage that ordinary cellular repair struggles to fix cleanly. The same kind of damage that is harder to patch than a simple, single break in the code. A crew asked to stay sharp through 7 months of transit, a full surface mission, and the trip home cannot afford that kind of erosion. And the people working this problem know it. 3 fronts are working against it. Pharmaceutical research, some of it built on drugs first developed for cancer treatment, is testing whether certain compounds help damaged cells repair themselves before the harm compounds, early results promising enough to keep the work funded. Materials research favors hydrogen, an element light enough to absorb and scatter cosmic rays without triggering the destructive cascade that heavier shielding invites. Polyethylene, plain water, and certain plastics rank among the best passive shields available, which is why some spacecraft designs wrap the crew's sleeping quarters in the ship's own water supply, shielding and life support sharing the same tank, water on one side of a wall doing double duty. And the boldest front is speed itself. Cut the transit from 7 months to something closer to 3, and total exposure falls by nearly half. The real argument behind nuclear thermal and nuclear electric propulsion research, quietly funded and advancing today, with more distant concepts like nuclear pulse propulsion and fusion drives waiting further down the road. The physics is understood. The engineering is enormous but not impossible. The politics of launching nuclear material off a planet remains its own unresolved question. There is something almost poetic underneath all of it. The same nuclear physics first unlocked in the 1940s for destruction, the same force that powers every star and forges the heavy elements inside a supernova, may end up being what safely carries a fragile human crew across the gap to Mars. The universe's most violent processes, the ones flinging cosmic rays at a spacecraft in the first place, redirected into carrying life instead of ending it. The radiation moves through the body in silence, and it is not the only silent thing happening to that body. Somewhere in those same weightless months, bone and muscle are quietly coming apart too, unnoticed until the day gravity comes back and asks for them. The mechanism is simple and merciless. On Earth, every step, every reach for a coffee cup, every shift of weight from one foot to the other sends a small mechanical signal through the skeleton, a nudge that tells bone-building cells to keep working, to keep depositing fresh material where the load lands. It is a service the body performs for free, powered by gravity, never billed, never even noticed. Take the load away and the signal stops. Bone-building cells slow down. Bone-dissolving cells do not. The skeleton begins losing material faster than it can replace it. Roughly 1 to 2% of bone mass a month in the regions carrying the most weight on Earth, the hips, the spine, the long bone of the thigh. 6 months of that and a crew member's bones can carry the density of someone decades older, a body in its 30s or 40s quietly borrowing the skeleton of someone twice its age. That would be a manageable cost if the crew could simply float their way to Mars and float their way home. They cannot. At the end of a 7-month transit, they still have to land, stand up, and work under Martian gravity, a pull of about 38% of Earth's. Picture someone who weighs 180 pounds standing on a bathroom scale back home. On Mars, that same person weighs about 70 pounds, roughly what a 10-year-old weighs on Earth. Lighter gravity sounds like a gift, a discount on the effort of simply standing up. For a skeleton that has spent 7 months forgetting how to bear weight at all, even a light pull is a demand it may not be ready to meet. A bill arriving on a body that spent the last 7 months assuming no bill was coming. Countermeasures exist, and they help. Protocols developed on the space station call for rigorous daily exercise, roughly 2 hours of it. Resistive machines that make muscles push and pull against real load, even with no gravity to supply it. And in some cases, medication that slows the bone loss further. Astronauts who follow the regimen faithfully lose meaningfully less bone than those who skip sessions. But the equipment takes up space and mass on a vehicle where every kilogram is already spoken for. Mass that could otherwise carry food, fuel, or spare parts. No amount of discipline fully stops the decline. Some of the loss is simply the price of the distance, a toll levied whether or not the crew pays attention to it. Bone is not the only system paying that price. Muscle mass follows a similar curve, wasting slowly without the resistance it evolved to expect. The legs especially, since walking and standing are the two motions weightlessness erases most completely. Cardiovascular fitness declines, the heart no longer pushing against gravity's pull on blood with every beat. So it grows lazy in a way that shows up the moment gravity returns, and blood suddenly wants to pool in the legs again. Fluids that gravity normally holds toward the feet drift upward instead, toward the head, leaving faces rounder and puffier than they should be, and raising pressure inside the skull, a change researchers suspect may alter vision over the long term in ways not yet fully understood. It is one more open question riding along on a 7-month transit that leaves little room for open questions. The clearest window into what a body like that actually experiences comes from a single astronaut. Scott Kelly spent nearly a full year aboard the space station, 2015 into 2016, while his identical twin brother Mark stayed on the ground, giving NASA something it had never had before: 2 genetically matched bodies to compare, one that flew and one that did not. What researchers found went further than bone and muscle. Kelly's telomeres, the protective caps on the ends of his chromosomes, changed length, stretching longer in orbit than his brother's on the ground. His gene expression shifted in ways nobody had predicted, thousands of genes turning on or off differently than expected. His cognitive performance showed subtle differences from his brother's, measurable but not severe, the kind of shift that would matter enormously to someone who has to think clearly during a landing. Most of it reversed after he came home. Not all of it. Not immediately. And Kelly had advantages a Mars crew will never have. He orbited close enough that Earth's magnetic field still offered him partial shelter overhead. Supply ships kept arriving on schedule. If something had gone seriously wrong, a capsule could have carried him home within hours. A crew bound for Mars gets none of that. No partial shield, no resupply, no hours-long trip home if a body starts failing in ways nobody predicted. None of this is told to frighten. It is told because these are the actual terms every crew member accepts. Eyes open, before signing on, having read the same studies and asked the same hard questions any of us would ask. And because every one of these problems already has people working against it. At NASA's Human Research Program, in university labs, inside private aerospace companies and agencies around the world, testing new drugs, refining exercise devices, hunting for the mechanism behind the vision, changes nobody fully understands yet. Science is not a destination. It is a process. And the process is moving. Still, knowing the process is moving does not undo the arithmetic waiting at the end of the transit. 7 months out, bones thinned, muscles wasted, a cardiovascular system that has forgotten what gravity feels like, and a vestibular system, the inner ear's own sense of up and down, that has spent the same 7 months floating with nothing to orient against. And after absorbing the radiation, after the isolation, after all of it, the mission does not pause to let a weakened body recover before asking more of it. It asks that same body to survive one of the most technically demanding maneuvers ever attempted, a passage so violent and so unforgiving that the engineers who designed it already have a name for it. They call it the 7 minutes of terror. That name is not exaggeration. It is a lower bound. Mars has spent the last 7 months growing in the windows, a reddish smudge becoming a disk, the disk slowly resolving into an actual world, dust storms visible now, polar caps sharp at the edges, canyon systems wide enough to swallow entire mountain ranges. In a matter of hours, not days, that world has to catch this crew and hold them gently, or it will not hold them at all. Days before entry, the crew and mission control, the delay now sitting near 20 minutes each way, work through a series of small corrective burns, nudging the trajectory toward an entry corridor so narrow it is measured in fractions of a degree, a margin about the width of a pencil tip held at arm's length. There is no correcting it once the atmosphere is reached. 20 minutes of delay means Earth would only ever learn what happened after it had already happened. So every last adjustment has to be finished and verified while there is still time for a reply. Too shallow, and the vehicle skips off the top of the atmosphere like a stone thrown flat across water, bounced back into open space with no second attempt. No fuel budgeted for a return trip through that same door. Too steep, and the heat wins in seconds. Between those two failures sits the only path that ends with anyone standing on the ground. Here is the part that makes Mars uniquely cruel to land on. A thinner atmosphere should mean an easier arrival, less air pushing back, less to fight through on the way down. Mars gives you the opposite. Its atmosphere is roughly 1% as dense as Earth's. thin enough to do almost nothing to slow a falling spacecraft, yet thick enough to generate spacecraft-destroying heat on the way through it. All of the heat. Almost none of the braking. The vehicle crosses into that thin air moving at roughly 20,000 kilometers an hour, 16 times the speed of sound, and has to shed nearly all of it before touching ground. Ground that at the most scientifically interesting sites sits low enough to have even less air overhead than the average. This has humbled engineers for half a century. Of every Mars mission attempted, Soviet probes in the early 1970s, the American Vikings, Pathfinder, the twin Mars exploration rovers, Phoenix, Curiosity, Perseverance, a significant fraction simply failed, crashed, or vanished without explanation. Those were machines built for exactly this problem, tested and refined across decades, and the atmosphere still beat a meaningful share of them. Those were machines. What is coming down through that thin orange air now is not. And the hardest part of the whole descent was still ahead. The sequence begins the moment the heat shield bites into the upper atmosphere. Plasma builds almost immediately, the compressed air around the vehicle heating past the temperature of the sun's own surface, the shield absorbing what it can and radiating the rest away. That glowing sheath blocks every radio signal for several minutes straight. No delay, no signal at all. Nothing gets through, not to Earth, not to anyone. The crew is sealed inside a fireball moving faster than any commercial aircraft will ever fly, able only to wait. No human reacts fast enough for what happens next, so no human is asked to. Onboard computers make the decisions instead, hundreds of them every second, adjusting the vehicle's orientation, managing the heat, staging the next phase before the crew has finished processing the last one. The crew are among the most highly trained people alive, and for these minutes, they are passengers, strapped in, trusting engineering they cannot see happening around them. As the plasma fades, the vehicle is still moving far too fast to land. Robotic missions solved this with enormous parachutes deployed at supersonic speed, and it worked. For a machine weighing about as much as a small car, a ship carrying a crew weighs dozens, sometimes hundreds of times that. Scale a parachute to match that mass, in air this thin, and the physics simply refuses. The canopy would need to be impossibly large, the forces of opening it at speed violent enough to tear the fabric apart in the act of trying to save the vehicle it is attached to. So the approach changes entirely. The plan built around Starship uses the engines themselves, firing against the direction of travel while still supersonic, pushing back with raw thrust instead of fabric and drag. It has already been demonstrated on Earth, Falcon 9 boosters descending tail first onto their own landing legs, a maneuver that looked like science fiction the first time anyone saw it succeed. But doing the same thing in Martian air, where the atmosphere pushes back with about 100th the force of the conditions those engines were tested in, is a different problem entirely. The engines have to fire reliably in a thinness no test stand on Earth can fully reproduce. NASA's own designs lean on a second idea alongside it, a large, lightweight, inflatable structure that balloons out behind the heat shield, to add drag without adding the weight of more rigid material, tested under a program called LOFTED, short for Low Earth Orbit Flight Test, of an inflatable decelerator, with results that have engineers cautiously hopeful. And all of this is happening to bodies that have not felt real weight in 7 months. The deceleration presses down at several times a normal body weight, sustained, relentless, not as brutal as a fighter pilot's hardest maneuver, but held far longer, landing on bones that have spent 7 months quietly losing density, on muscles that have spent 7 months forgetting how to push back. The inner ear, floating that entire time with no up or down to measure itself against, is suddenly asked to make sense of both again, all at once, under crushing load. Whether a crew in that condition could actually respond if something went wrong, override a computer, read an instrument, think clearly while their own inner ear is screaming false alarms, is not settled. It remains an open, actively studied question with real design consequences. One proposed answer being to save the most demanding surface work for a few days after landing. Once the body has had a little time to remember gravity, to let the bones and the balance catch up before asking more of them. Emergencies, of course, do not wait for a recovery schedule. If every one of those steps goes right, deceleration on target, engines firing, orientation correct, the landing legs unfold in the final seconds and take the remaining weight. Then the engines cut off. The dust they just threw into the air begins to settle. The vibration stops. The noise stops. And in a silence more complete than anything this crew has heard in 7 months, something extraordinary has happened without ceremony. A vehicle carrying living human beings is sitting on the surface of another planet. For a moment, nobody speaks or moves. Instruments report their numbers to an otherwise empty cabin. Then someone laughs or cries or both, because in 4 billion years of life on Earth, no one has ever done this before. But landing was never the finish line. It only closes one set of dangers and opens another. A habitat that has to be checked and sealed before anyone can breathe easily inside it. Food and water and oxygen that now have to be managed with no margin for error. A chemically reactive dust that will find its way into everything no matter how careful the crew is. Suits that must work perfectly every single time someone steps outside. Because a single failure out there kills in minutes, not hours. 7 months of transit, radiation, a slowly dissolving skeleton, and a descent that has just tried to shake them apart, and none of it was the actual point. It was only ever the price of admission. And beyond all of that price, the question this whole mission was actually built to answer is waiting in the rock under their boots. Is there, or was there ever, any sign of life? The silence after touchdown does not last. It breaks in the most ordinary way imaginable. A checklist. Not a ceremony. Suit pressure verified. Seals checked, then checked again. Gloves sealed at the wrist, helmet locked and tested. The airlock cycles down toward the near vacuum waiting outside, air bleeding away in stages, and somewhere in that quiet, a gloved hand finally closes around a handle. The door swings open onto another world, and nothing about the moment announces itself. It just happens. One item on a list, finished, and then the whole of Mars is standing right there. Years of training led to this exact motion, a hand on a handle, and none of it prepared anyone for what the color of the sky would actually do to them. What waits on the other side is not the darkness some of the crew half expected, and not the harsh bleached light either. Mars has a sky doing something strange and beautiful. A pale, dusty butterscotch, somewhere between tan, salmon, and the deep orange of a late autumn afternoon. Fine iron oxide dust hangs suspended in the thin air overhead, and it scatters light in a way Earth's atmosphere never does, wrapping the whole landscape in an otherworldly amber glow. It is the first thing every account of this moment comes back to. Not fear, colour. The sun still hangs up there. Smaller than the one this crew grew up under, Mars sits roughly 50% farther from it than Earth does. So it shrinks down to a sharp white point, one you still cannot look at directly, ringed by a warm, dusty halo. On Earth, sunset burns red, orange, gold, the sky catching fire on the way down. Mars does the opposite. As the sun sinks toward the horizon, the same dust that turns the daytime sky orange begins scattering shorter blue wavelengths instead, and the sky around the sinking light blooms into a pale, ethereal blue. Curiosity photographed that blue years earlier, a machine's camera catching it from a distance, and it was already breathtaking through a lens millions of miles away. Watching it happen in person, standing in the dust as the light turns, is something else entirely. Not the red farewell a lifetime of Earth sunsets prepared them for. A cold, delicate blue. The exact inversion of home. The land stretching out beyond the hatch is difficult to read at first, and not because it is empty. It is vast in a way the eye has no tools for. No trees, no buildings, no telephone poles marching toward a horizon, none of the small ordinary objects a mind uses without thinking to judge how far away something sits. What is left is rock, dust, and a horizon that arrives sooner than it should, because Mars is only about half the diameter of Earth, and the ground curves away faster underfoot than it ever did back home. Rocks are scattered everywhere across that shortened horizon, thrown up and shaped across billions of years of impacts. Old volcanism, long vanished floods, and slow, patient erosion. Some look almost familiar, dark basaltic stone not so different from a Hawaiian lava field, the kind of rock a geologist could name on sight. Others do not fit anywhere in that memory, rounded, smoothed, worn by processes still being worked out. And the ground itself is not the soft powder imagined from a distance, but a mix of fine dust, coarser grit, and rock underfoot, sometimes surprisingly firm, sometimes not. That dust is not harmless. It is fine, rust-colored, and it settles onto everything it touches: boots, seals, camera lenses, and unlike dust on Earth, it is chemically active. The Martian surface is rich in perchlorates, oxidizing compounds toxic to the human body in enough quantity, interfering with thyroid function, present here at concentrations any environmental standard on Earth would call hazardous. It clings by static charge to gloves and fabric, and it does not brush off the way garden dirt does. Getting it inside the habitat, into a suit seal, anywhere near the crew's own biology, is not a housekeeping problem. It is a health problem, managed the way a hospital manages contamination, dedicated airlock routines that brush and vacuum suits before anyone steps back inside, strict cleaning protocols, suits built specifically to leave as much of it outside as possible. Every return through that hatch is its own small procedure, repeated without exception for as long as anyone lives on this ground. But the dust is not the part of this world that can kill fastest. Average surface temperature here sits around minus 60 degrees Celsius, colder than anywhere permanently inhabited on Earth. That average hides a swing of its own. Near the equator, on a clear summer afternoon, the reading can climb to nearly 20 degrees Celsius, briefly close to a mild spring day back home, warm enough to almost forget where you're standing. Then the sun goes down. Within hours, the number falls to minus 70, minus 80, minus 90, because the atmosphere here is too thin to hold the day's heat, and it bleeds away into space almost as fast as it arrived. No blanket of air to trap it, nothing to slow the loss. Anyone caught outside after dark in a failing suit would not survive long. Cold is still not the sharpest edge of this place. Outside the suit, the pressure sits at around 600 pascals, less than 1% of what the human body is built for at sea level on Earth. Without the suit, the moisture on your eyes would begin to boil away. The gases dissolved in your blood would start to bubble. You would lose consciousness within seconds. You would be dead within minutes. The suit is not clothing. It is not simply protection against the cold. It is a portable life support system, sealed and total, the only thing standing between a living human being and a world offering no margin at all for a mistake. It has to work every single time, with no exceptions, because out here there is no version of a small mistake. And still, knowing every part of that, the crew steps outside anyway, day after day, suiting up for a world that would kill them in minutes given the chance. Not recklessness. The reason for coming this far is standing right in front of them, in the rock. A trained geologist can look at an outcrop, chip a sample, hold it to the light, turn it over, weigh its texture and color against years of field experience, and make an instant judgment call that would take a rover, steered from millions of miles away with a communication delay of its own, weeks to approach with the same caution. A rover can drill, a rover can photograph. A rover cannot notice, cannot follow a hunch, cannot glance sideways at an outcrop that does not quite fit the pattern and decide on instinct that it is worth a closer look. Human hands, human eyes, human curiosity, instruments no machine yet built can fully replace. That is the argument, in the end, for sending people instead of only sending robots. And it is the reason this crew is out here at all. Boots in the dust of a world that would rather they were not. And the questions waiting in that rock have been sitting patiently for longer than anything else this crew has ever touched. Longer than any building, any language, any human idea. They are old questions. And out here, standing on ground no living person has stood on before, the crew is finally close enough to start asking them properly. Those old questions do not wait patiently. They have been sitting in the rock for billions of years, and the oldest of them all is also the largest one this mission was ever built to ask. Did life ever touch this world? A trained eye is good for more than picking the next outcrop to sample. Point it the right way and it turns 4 billion years of geological silence into something close to a conversation. An instrument no rover carries and no camera can replicate. Mars was not always this dead and reddish. Orbital and rover data going back decades tell a stranger story. Somewhere between 3 and 4 billion years ago, in a period geologists call the Noachian, water ran across this surface. Not scattered puddles, rivers, lakes, quite possibly an ocean, spread wide across the northern lowlands, sitting there while Earth's own oceans were already alive. The evidence does not lean on one instrument or one place. River valley networks are carved into the southern highlands, the unmistakable signature of water that flowed for long stretches of time, not a single flood. Craters hold layered sediment, the kind that only settles slowly at the bottom of standing water, and certain minerals, clays, carbonates, sulfates, form only in the presence of liquid water. 3 separate lines of evidence, one answer. Somewhere on that wetter, younger Mars sat a lake inside what is now called Jezero Crater, fed by a river spilling sediment into it through a delta still visible from orbit today. On Earth, river deltas are extraordinary at trapping and preserving organic material, the chemical building blocks of life, sometimes the fossilized remains of life itself. Jezero's delta is built from that same kind of sediment. It sat at the bottom of a lake for what may have been millions of years. If single-celled life, the kind that ran Earth's biology for its first 2 billion years, ever took hold on Mars, a delta-fed lakebed is exactly where you would look for it. Perseverance has been drilling narrow cores from the most promising rock in that delta, and sealing each one inside a titanium tube. The rover cannot run the analysis those cores need. A future joint mission between NASA and the European Space Agency, called Mars Sample Return, is meant to bring them home to laboratories no rover could ever carry inside itself. The plan has slipped, argued over, redesigned more than once. But the samples are not hypothetical. They are sitting on the surface of Jezero Crater right now, sealed, waiting. This is where a crew changes the math. A rover crossing a few kilometers takes years, checking every move against a communication delay. A geologist in a pressure suit could cross that same ground in a single day, pick up a rock, turn it in a gloved hand, read its color and grain and texture, and decide on the spot whether it is worth keeping. Some of the most important discoveries in Earth's own geological record came from exactly that kind of moment. A scientist glancing somewhere unplanned and noticing something that did not fit. No algorithm has ever been built that flags a hunch. And still, after all of that, the honest answer is the one Mars has given for 50 years of searching. We do not know. Anyone claiming certainty in either direction is saying more than the evidence supports. What can be said plainly is this: Mars had liquid water for long stretches while life was already established on Earth. Both worlds formed from the same cloud of material, in the same neighborhood, at the same time. The chemistry life runs on here: carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur was present there too. The conditions understood to matter were in place. That is not proof. The step from chemistry into biology remains one of the least understood events in all of science, on Mars or on Earth, which is why either answer would be enormous. Find one fossilized microbial mat, one clear biosignature, a chemical trace that only biology leaves behind, buried in 3 billion-year-old lake mud. And it means life is not a freak accident confined to a single blue planet. It means life tends to happen, given water, chemistry, and time, wherever those 3 things line up. Wait, finding nothing would matter almost as much. Search every promising rock this crew and every rover before them can reach and come up empty, and that silence would be almost as loud as a discovery. Not disappointment, evidence that the leap from chemistry to biology is rare, that something happened on Earth that does not happen easily elsewhere, and that we may be lonelier in the universe than we have let ourselves believe. Either way, the search reshapes what we understand about our own existence. The question is not only about the deep past, either. There is a real, if narrow, possibility that something is alive on Mars right now, not on the surface, scoured by radiation and laced with toxic salts, but far beneath it, where geothermal heat could keep water liquid under kilometers of rock, sealed away from the worst the surface endures. Those are the same kinds of hidden places. Deep crust, hydrothermal cracks, salty pockets of trapped water where life persists on Earth in conditions that would kill almost anything else. Europe's Mars Express orbiter has picked up radar signals that some scientists read as liquid water hiding beneath the southern polar ice. Other scientists read the same data differently. The debate is unresolved. It is a live one, not a closed one. That possibility carries a weight of its own. If something is alive down there, even something microbial, even something ancient and barely clinging on, this crew would be walking in carrying trillions of organisms of their own, on their skin, in their lungs, on every surface they touch. No amount of scrubbing makes a human being sterile. International rules, called planetary protection, already govern how carefully robotic missions must be cleaned before launch. A crewed mission multiplies that problem past anything those rules were built for. Contaminating a native Martian biosphere before anyone had even confirmed it existed would be one of the great scientific losses imaginable. An answer erased before the question was fully asked. There is no clean solution to this yet. Only the responsibility to move carefully, because the ground under those boots might not be as empty as it looks. Step back far enough, and the whole search becomes something larger than biology. The rock this crew is kneeling over settled to the bottom of a lake 3.5 billion years ago, when the universe itself was only about 2/3 its current age, when the sun was younger and more volatile, when Earth was still a shallow, simple world of early cells figuring out how to survive. That rock has been waiting since before complex life existed anywhere we know of. And now, billions of years later, descendants of those same early cells have crossed tens of millions of miles to kneel down and ask it what it remembers. We are the universe looking at itself, not as a phrase, as a literal description of what is happening in that moment, atoms that eventually organize themselves into curiosity, standing over atoms that never got the chance, both forged inside the same dying stars, both waiting billions of years for someone, anyone, to ask the question out loud. The answer is still not in, but the asking does not stop when the sun goes down over Jezero crater. It just moves indoors, into a small crowded habitat, into the next ordinary day. Indoors, 4 months into the surface stay, that next ordinary day looked like nothing the mission plan had ever bothered to name. Not a launch, not a landing, not a single headline moment, just a Tuesday. The adrenaline that carried the crew through descent and those first trembling steps outside had long since faded into something quieter, a working rhythm. They knew the habitat the way you know your own apartment. Which panel rattled when the heating cycle kicked on, which crewmate hummed while working, and which one went silent under stress. The Martian day, a soul, runs 24 hours and 37 minutes. Those extra minutes do not sound like much. Stack them across weeks and months, and they quietly pull the body's clock away from anything Earth ever taught it. A slow drift no alarm clock can correct. The habitat itself sits at the edge of comfortable. Current concepts favor something roughly cylindrical, sometimes inflatable, built to squeeze the most livable volume out of the least mass a rocket has to lift. What is left after equipment, life support, instruments, and medical supplies claim their share works out to something close to a small studio apartment, per person, shared with 5 other people for the better part of 2 years. Privacy barely exists. Every cough carries. Every mood shows. Earth hands out air and water without asking anything in return. Mars does not, so the ship has to build both. Oxygen comes from splitting water molecules apart with electricity, a process called electrolysis, or from pulling carbon dioxide straight out of the thin Martian atmosphere, the way Perseverance's MOXIE experiment already proved possible, the Mars Oxygen In Situ Resource Utilization Experiment, a rover-sized demonstration that quietly answered one of the largest engineering questions a crewed mission would ever ask. Water gets no easier treatment. Every breath of exhaled moisture, every bead of sweat, is captured, filtered, and returned to the loop. The station in orbit above Earth already recycles more than 9 of every 10 drops that pass through it. A Mars-bound system has to do better still, because out here nothing extra is coming. Food offers less comfort than either. The bulk of it rode along from Earth, calorie-dense, shelf-stable, engineered to survive years in storage, and still deliver everything a working body needs. What it cannot deliver is variety, and the psychological weight of eating the same limited rotation of meals for months is well documented among people who never got a say in what shows up on the tray. It sounds like a small thing until you have opened the same dozen pouches on rotation for the better part of a year, and researchers who study isolated crews take it seriously precisely because it sounds small. Some habitat designs answer with a small hydroponic garden, a shelf of greens and herbs growing under grow lights, contributing almost nothing to the calorie count and almost everything to morale. Something alive to tend. Something that did not arrive sealed in a pouch 2 years earlier on a different planet. A single fresh leaf, torn off and eaten standing at the counter, can matter more to a person's mood that day than any calorie chart would predict. Then, there is the work outside. Suiting up for an EVA alone takes hours. Every seal checked, every system verified twice, a ritual with no shortcuts because a missed step out on the plane has no second chance behind it. Once outside, the suit becomes both a lifeline and obstacle, thick gloves flattening a sense of touch, joints resisting every reach and grip. Geologists who train in Mars analog suits in the Canadian Arctic and the Arizona desert report the same thing again and again. Simple tasks, picking up a rock, framing a photograph, turning a wrench, take 2 or 3 times longer than they would with bare hands. Every excursion runs on a clock set by the suit's own oxygen and battery reserves, planned to the minute before the hatch even opens, and watched the whole way through from inside by a crewmate ready to guide it or call it off. It would be reasonable to assume Mission Control is still running the show from Earth, the way it always has. It is not. The communication delay, still roughly 20 minutes each way at this distance, makes real-time oversight impossible. So the crew decides, acts, and reports rather than asks and waits. That is a genuine break from everything spaceflight has done before this mission, and the weight of being the final authority on your own survival sits on top of everything else the day already demands. Above them, the sky keeps doing things no sky on Earth does. Dust devils spiral across the plains on warm afternoons, spinning columns of rust-colored grit that can climb hundreds of meters, roughly the height of a 40-story building, before dissolving as quickly as they formed. 2 moons cross the same sky, and neither behaves the way a moon should. Phobos is close enough and fast enough that it rises in the west and sets in the east, crossing from one horizon to the other in a few hours. Deimos, smaller and farther out, barely outshines a star. Seeing both at once is wrong in a way that never quite stops being wrong, no matter how many nights you spend under it. The clearest nights are the strangest. With the dust settled and the atmosphere too thin to blur anything, the stars burn with a steadiness Earth's turbulent sky never allows. No flicker, no twinkle, just a hard and constant light. The Milky Way arches overhead like a band of cold fire. And somewhere in that sky, exactly where you learned to look on the very first night, sits a small blue-white point that used to be the whole world. Not a crisis, not an alarm, not a single warning light on any panel, just a Tuesday night, and a point of light holding every person you have ever loved, every ocean, every song, every argument that ever mattered, compressed into a single pixel. On the space station a few hundred kilometers above Earth, the planet still fills half the sky. Out here, it does not. Out here, it is small enough to vanish behind an upraised thumb, and that is the version of the overview effect nobody quite prepares you for. Researchers who study Antarctic winter rover crews have watched this exact ache before. Early in an isolation deployment, thinking about home helps, it motivates, it comforts. Later, the same thoughts start to hurt. A child's school play or a neighbor's new dog described in a message from home can feel like it is arriving from another universe entirely. close enough to read about and impossibly far to reach. The clinical term for the fatigue and emotional flatness that can creep in during prolonged isolation is asthenia. Mission psychologists watch for it constantly, tracking mood, sleep, and small shifts in how a crew member talks in daily check-ins. The honest answer is that none of the countermeasures, private time, scheduled calls, virtual reality walks through a forest or a beach, fully solve it. They soften the ache. They do not remove it. What holds against that ache is not a program or a pill. It is the planet itself. No Antarctic researcher, however isolated, ever stepped outside into a world no human eye had seen in person. A world carrying 3.5 billion years of geological and possibly biological history in every rock underfoot. Every excursion here is a walk through deep time most of humanity will only ever read about. That privilege gets felt again every single day, in small, unremarkable moments, as much as large ones, in the dust on a glove, in the particular color of the evening light, and it does something steadier and quieter than excitement ever could. Astronauts and researchers keep returning to the same word when they try to explain what actually gets a person through months like this. Purpose. Not extroversion, not raw resilience, but a clear sense of why they are here. The crews who hold together best on long isolated deployments are rarely the ones who seem toughest on paper. They are the ones who never lost track of the reason. Viktor Frankl, a psychiatrist who survived years in Nazi concentration camps, argued that a human being can endure almost any how as long as the why is strong enough. This crew carries one of the strongest whys anyone has ever taken off a launch pad. They are not just enduring out here, they are pioneering. And somewhere past the dust devils and the 2 crossing moons, past the point of light that used to be the whole world, that soul was already turning toward the day this mission would have to start pointing itself back the other way. The turn is never sudden. It begins as a schedule on a screen, the return window opening only when the planets slide back into the alignment that makes going home possible. And it arrives inside all 6 of them at once as a knot of relief, terror, grief, and anticipation that no training program fully prepares a person for. The same purpose that carried them through the surface stay does not switch off now. It simply turns around and starts pointing toward home. Going home means trusting the engineering all over again. It means another 7 months of deep space transit stacked on top of everything already spent. More radiation, more bone loss, more isolation, and it means returning as someone the crew cannot fully picture yet, changed in ways nobody fully understands, because nobody has ever done this before. There is no version of this mission that ends with the same 6 people who left Earth. There never was. Departure day looks nothing like the send-off waiting for them back on Earth. No crowd, no countdown, no cameras, just the crew, the habitat, the rust-colored plane outside the window, and a spacecraft that has sat waiting on the surface for over a year. The days before are consumed by checklists, samples loaded, equipment secured, the departure list run down item by item with the same care that got them here alive in the first place. Somewhere inside that routine, each of them finds a private minute, at a window or out on the ground, because they know something no one who comes after them will ever know quite the same way. What it is to be first. To stand where no member of the species had stood before. To see a landscape human eyes were seeing for the first time in the entire history of life on Earth. That stays with a person for the rest of a life. The machine that lifts them off the surface bears almost no resemblance to the one that shook them off Earth. Mars holds its surface with a far gentler pull, and its atmosphere is too thin to push back against anything moving through it. No 5,000-ton stack is needed here. No booster catch, no tower arms reaching out of the dark. A single, far smaller ascent vehicle is enough, climbing to meet the Earth return ship that has waited quietly in Mars orbit since the day they landed. The engines fire. The ground falls away. Within minutes, not the long, crushing minutes of an Earth launch, the crew is in orbit above a world they will probably never see again. Probably. Because the first humans to reach Mars will almost certainly not be the last. If this mission succeeds, if the data and the samples and the plain human testimony make it home, the next crew will be in planning before this one has even landed. Every answer here tends to raise 10 new questions, and every discovery reshapes the map of what is still unknown, until standing on Mars is no stranger to the world than a research team wintering over in Antarctica. This crew is not closing a door behind them. They are the ones who first proved it opens. From orbit, the burn that turns them back toward home barely announces itself. No roaring stack beneath them. No max Q shaking the hull. No plasma sheath swallowing every signal for minutes at a stretch. Just a long, steady engine burn. The trans-Earth injection, tipping the ship out of Martian orbit and onto the slow curve back. Then, again, silence. Again the stars. Again months of transit stretching out ahead. It would be reasonable to assume the hardest leg of this journey is already behind them, that reaching toward the unknown is what truly tests a person, and coming home is simply relief. Research on long-duration missions suggests otherwise. Outbound, every day had closed the distance towards something no human being had ever done. Homeward, that thing is already done. What is left is not discovery. It is only distance. 7 more months of weightlessness. 7 more months of radiation ticking quietly through the walls. The same small spacecraft. The same 5 other faces. And no grand unknown left to pull anyone forward. Only home, familiar and longed for, and still impossibly far. The goal stops being measured in miles. It gets measured in months, and every one of them can feel too slow. By the time the engines cut off for the last time, the numbers add up in ways no medical team has ever had to reconcile before. 7 months out, well over a year on a world pulling at roughly a third of Earth's gravity. Better than nothing. Nowhere near enough. 7 months back. 14 months in transit alone, spread across 2 long crossings, stacked on top of accumulated radiation, thinned bone, wasted muscle, a cardiovascular system that has half forgotten what full gravity even asks of it, and eyes that may carry subtle changes researchers still do not fully understand. Scott Kelly needed months to feel like himself again after a single year in low orbit, and he still had partial shielding from Earth's magnetic field, and a way home measured in hours if something had gone wrong. This crew carries none of that cushion behind them, and their reconditioning, walking under full gravity for the first time in years, arrives joyful and physically demanding in the same breath. Assessment, monitoring, and slow rehabilitation will stretch on for months, in some cases years, long after the cameras and the headlines have moved on to whatever comes next. The harder adjustment is not physical. It would be reasonable to think that once the body heals, the ordeal is over. It is not. Researchers who study returning astronauts and Antarctic expeditioners have a name for what comes next. Re-entry shock. Not the atmospheric kind, but the disorientation of stepping back into an ordinary life after living somewhere extreme. For a crew that walked on another planet, searched sediment 3.5 billion years old, watched a sunset turn blue over a frozen desert, and saw Earth shrink down to a single point of light. That gap is not small. No debrief, no support group, no amount of professional care fully closes the distance between all of that and standing in a grocery store, a cereal box in each hand, trying to remember why the choice once felt easy. And yet, almost embarrassingly, people adapt. The same flexibility that let this species take root from the Arctic to the tropics. From small bands following river valleys into unknown ground, to cities holding millions of strangers, goes to work again here. Slowly, unevenly. With rough edges some of them may carry for good. It works, in the end, because the pull toward the people, the places, and the small, unremarkable rituals of an ordinary life is stronger than almost anything else a human being can feel. What they carry back is not only samples sealed in titanium and years of collected data, it is a story that reaches back much further than this one crew and further than this one small planet. Wider than a planet means starting before the planet existed at all. 4.5 billion years ago, there was no Earth and no Mars, only a cloud of gas and dust drifting cold and formless in the dark, until gravity did what gravity always does, pulled the loose material inward on itself, tighter and tighter, until the pressure and the heat at the center lit a fire that has not gone out since. Our sun. What was left over spread into a wide, flat disk around that new fire, and inside the disk, grains of dust and specks of ice found each other. Stuck, grew, collided, grew again for millions of years. Dust becoming pebbles, pebbles becoming rocks, rocks becoming worlds. One of those worlds happened to settle at the one distance from the new sun, where water could stay liquid on a surface instead of freezing solid or boiling off into space. That single accident of position is the only reason any of the rest of this story happens at all. On that world, roughly 3.5 billion years ago, something occurred that is still, today, the least understood event in the history of science. In shallow, warm water, maybe at the edge of an ocean, maybe around a scalding vent on the seafloor, chemistry became biology. A molecule learned to copy itself. Then another. How that happened, exactly, nobody fully knows. Not yet. And whether it happened here only once or many times over is one of the deepest open questions any scientist can ask. Every laboratory attempt to recreate that first step has come close and then stopped short. Close enough to see the outline of an answer, not close enough to hold it. From that first fragile, forgettable, self-copying molecule, everything followed. Cells that learned to pull energy from sunlight and, without meaning to, filled the air with oxygen. Cells that grew more complex, then learned to cooperate, then became bodies built of many cells at once. The first animals, the first backbone dragging itself out of the water and onto dry land. Dinosaurs for well over 100 million years, until an asteroid struck 66 million years ago and rewrote everything that came after. Small mammals in the wreckage that followed. Then primates. Then something that could finally ask why. 4.5 billion years. An unbroken thread. Every single ancestor anyone has ever had. Confined the entire time to one planet. Through ice ages and floods and asteroid strikes and everything else that could have severed it and did not. Not once broken. Not once did anything in that whole chain leave. Until this generation. That is the hinge this entire journey turns on. Somewhere along that unbroken thread, one of its products figured out how to build a machine capable of escaping the gravity of the world that made it, crossing the dark gap between two planets, setting down on the surface of another one, and walking on it. Every ancestor anyone has ever had lived and died on this one world. Every species in the whole history of terrestrial life has been sealed inside it. Show this moment to any of them, to anyone who ever looked up and wondered about that reddish point of light drifting against the stars, and it would look like a miracle. It is not supernatural. It is something more ordinary and in its own way more remarkable. Curiosity that refuses to accept a question is too hard, too far, or not worth asking. Here is the largest way to say what that curiosity is actually for. The universe is roughly 13.8 billion years old, longer ago than the number itself is easy to hold in the mind. For most of that time it was dark, not because it lacked stars or galaxies by the hundreds of billions, but because none of it was being watched. Supernovae detonated with nothing to see them. Galaxies collided in total silence. Deep time piled on the deep time with no mind anywhere to register any of it happening. Then, on one small rock, circling one ordinary star, at the edge of one ordinary galaxy among hundreds of billions, something changed. Eyes opened. Questions began. We are the universe's way of knowing itself. That is what an astronomer squinting through a crude early telescope at a moving red point of light was doing, centuries ago. It is what a scientist bent over a microscope, studying some stubborn organism pulled from a scalding deep sea vent, is doing. It is what a spacecraft falling through a plasma blackout toward an unmapped landing site is doing. All of it is the same impulse, scaled up, pointed outward, given rocket engines and sample tubes. Carl Sagan put it plainly, that we are a way for the cosmos to know itself, that our science and our art and our love and our longing are the universe experiencing itself through us. When the first boots finally press into that rust-colored dust, they carry more than one crew of 6. They carry every child who ever wondered what that light in the night sky was, every mapmaker who sketched shapes onto its surface and got them wrong, every engineer who lost a night's sleep over one stubborn line of guidance code, all of it standing, in a sense, together in that thin butterscotch light. And there is one more layer underneath all of it, quieter than the rest, and more intimate. The carbon in a human body, the iron carried in the blood, the calcium built into bone, none of it was made on Earth. It was forged inside stars that lived and burned and died long before our sun existed. Stars that exploded and scattered their insides across the galaxy. And some of that scattered material eventually drifted into the cloud that became our sun, our planets, and us. We are the universe looking at itself with the very atoms the universe made. Mars is built from that same scattering, the same stellar wreckage, the same beginning. Not a stranger. Kin. So the truth that closes this whole journey is not that leaving Earth means leaving home behind. It is that home was never only Earth to begin with. Going to Mars does not abandon home. It stretches the word until it holds a little more of the universe inside it, which means everything this journey has been about. The fire and arithmetic of launch, invisible radiation ticking through the dark for months on end, a body slowly forgetting what Earth's gravity felt like, 7 minutes deciding everything, dust and cold and a sky the wrong color, rock that may or may not be holding the oldest secret in the solar system, an ordinary Tuesday, a point of light that used to be everything, the long ache of the way home. None of it was ever really a story about engines and heat shields. Technology was only ever the means. The real story is older than any rocket, older than any civilization, the part of a person that looks toward a horizon and cannot simply leave it alone, that keeps asking questions before it has the tools to answer them, that keeps sending fragile bodies and stubborn curiosity out into the dark, not because it is easy, not because it is safe, but because that is what we are. The first humans who actually walk on Mars have probably not been born yet. Some of them may be children right now on some ordinary evening, looking up at an ordinary sky, feeling a pull they do not yet have a name for. They will meet problems nobody has thought to plan for. They will solve them anyway, the way every generation before them solved the ones that once looked unsolvable. And then they will go, because we are already building toward it now. One failure and one correction, and one small breakthrough at a time. The same unbroken thread still moving, still reaching outward, still wondering. Nobody alive today will see how the story ends. And that has never once stopped anyone from starting the next chapter of it. The cosmos is vast. The questions are deep. And somewhere past the dark, still unanswered, they are waiting.